Good. Thank you for clearing that up. So, tomorrow we'll do a tutorial on these lessons, okay?
But the coursework deadline is today.
Today?
It is? I didn't know, but I didn't know what is deadline, so I don't know.
Whatever it is on Moodle.
Okay.
I put it on Moodle. It says it on Moodle.
Thursday, 13. 13 days.
I thought so, yeah. I thought I made it the 30th, the end of the month.
And the Kono sent us the mail, like, he said, like, coursework need to send to someone.
No, the other teachers, they give their coursework to Sylvia, but I do all my coursework on Moodle.
So we don't have
So
to...
no, you just give it to me on Moodle. It's easier.
Good.
Because with Sylvia, you have to print it, and it's a problem. So it's, I'm trying to be helpful.
Good. Because I teach one of my friends who study in business, the coursework.
Yeah, well, if their maths teacher is Joan or Carmen, then they have to give it to Sylvia. But my students, like you, and the science students, they give it to me on Moodle. Okay, stationary waves. You got that? Yeah? Okay. So, a few things to do. What is a standard wave or a stationary wave? So it's a wave that oscillates in one constant position, and it can arise in a stationary medium as a result of interference between two waves traveling in opposite directions. So what the heck does that mean? Let me show you. I'll try and draw a picture, okay? So imagine you have a string, and it's tied to the wall, and you move this end of the string up and down. So what happens is you get a little wave. Okay, and the wave moves along. And then what happens when it hits the wall? It will hit the wall, bounce and move back. Yeah? Now if you're still moving like this, you can make another wave come along. This one's going to the right and this one's going to the left. So the two will come along, and maybe in this picture, what do you think will happen? I think they'll cancel. Yeah? Because this one is a trough and this one is a crest. So I think when they meet, they'll cancel. Okay? But what you could do is you could have the wave like this. Make it equal to the full length. So what happens when it hits the wall and bounces, it comes back this way. And then it starts again. So what happens is you have something that looks like this. It looks like an 8. It's going up and down really quickly. Looks like infinity, yeah. Now, I can get you, there's a nice video here on YouTube, I can show you this. So you can do this with just a string. I'll try and show you. Where's search?
I heard the song.
Right. That sounds so terrible. Stand. Space. Can they do it? Let's see. I don't know. Let's see if they can make it.
For this demonstration, I have my able assistant Parker. Parker, smile at your admiring audience. And we will be demonstrating transverse standing waves. I'll also demonstrate traveling transverse waves. Here's a traveling wave. I'm starting the wave by creating a disturbance here with...
Try to jump. Come on. Come on. No, you're not good. I'll try someone else. This looks like it could show you. What the heck? Is this an ad? Oh yeah, good. So, okay. So that's just a little machine for making the wave. This is French. Probably says don't touch. There you go. So that's a standing wave. There's another one. You can see? Yeah? There you go. Nice. Okay, get the idea? So these are called standing waves. So they look like they're in one place standing, but they're really going up and down really quickly like this. Okay, so here's a picture of the machine that can make one. I would like you to write this down, please. You got that? You got that? Yeah, continue? Yeah? Okay. So, there's different parts of the wave. So you see this part here looks like it vibrates a lot. Whereas this part here, it doesn't look like it's moving. You know, it looks like it's fixed. So we have things called node and antinode. A node is the point where it has the minimum amplitude, no amplitude. So we call this point here the node. And the antinode is the point on the standing wave where there is a maximum amplitude. So this part here is called the antinode. And here it is in the picture. These red ones are the nodes, and then these blue ones are called the antinodes. Okay? So you have a choice. You can either write this or draw this. One or the other. I think you're all. Oh, interesting. Ben is going for drawing. Gow is going for writing. Summer is going for drawing. Got that? Yep. Okay. Next. So, let's imagine we know the distance between the antinode and the node. We'll just call it D. Okay? No, did I say? Oh, the distance between nodes or antinodes, sorry. So, let's imagine you know the distance between the antinodes. We'll call that D. Alright, what does the wavelength equal? What would that equal? Would it equal D? A half D? 2D? What would it be? The wavelength?
Half D.
Half D? No, 2D. Because this D is from here to here. That's only half the wave. You still need this piece and this piece for a full wave. See, this is a full wave. So the wavelength will always be twice the distance between the antinodes or the nodes.
I didn't know that.
Let's have a look again. So here's the wave. Oh, sorry. You know this distance from here to here. Can you see that that's only half a wave?
Yeah.
Because the full wave would be this.
Mm.
So your wavelength is equal to twice that distance. Yes? No? There's one wave. Okay. And the distance between the antinodes is only half of it.
Oh, okay.
Yeah? So if you know the distance between the nodes or the antinodes, then it's very simple to know the wavelength. It's just twice this distance. Is that okay? Are you sure? Okay. Now, if a string is held at both ends, forcing zero movement at the ends, then the ends become zeros or nodes of the wave. The length of the string then becomes a measure of which the string will entertain. The longest wavelength is called the fundamental. So I have to draw a picture of this. I wonder if I have one on the next page. Yeah, I do. So, look, I'll explain here with the picture. It'll be easier for you. Okay? You see this string here? This is the biggest wave you can make, right? Because, for example, let's say that's 1 meter. Then the wave would equal 2 meters in its wavelength, because the wave is like this. You know, this is only half the wave. This is the biggest wave you can make. This is the next wave you can make. You can't make this wave because you need to hold the string at the end. So this wave is smaller, right? If this is 1 meter, then the wavelength is 1 meter. Okay, if you look at this picture, if this is 1 meter, what's the wavelength?
2 over
2 over 3. Yeah, 2 over 3 meters. And if this is 1 meter, what's the wavelength now?
0.5 meters.
0.5 meters, okay? This is the biggest one. This is called the first harmonic, and it's also called the fundamental. I'll show you this here in the last one. The longest wavelength is called the fundamental. Oops, sorry. Okay, so this guy is called the fundamental, or also called the first harmonic. It's the second harmonic, the third harmonic. So I need you to write this down, but before you do, you need to also write beside this, also called the fundamental. Okay.
Oh,
And this only is for a string, where this side and this side, can you see in the picture? They're fixed. Okay. You don't have to do 4. Just do at least 3 of them, okay? You got that? Yep. Ben's okay? Continue? Yeah. Now, this doesn't have to be just for strings. It also works for air inside pipes, like when you're playing an instrument. When a sound wave is formed in a pipe, there will always be a note at the closed end and an anti-note at the open end. So, for example, I'll draw that here. If you have a pipe, and it's closed here and open here, this one is always a node, always, and this one is always an antinode. So you could have a wave like this. Okay? If it's, for example, open and open, then you must have, again, open means antinode, so you could have a wave like this. As an example, there are antinodes here. And, well, I don't really think this is possible. Closed and closed, no, it's just these two. Closed and open, and open and open. Antinode, antinode. Okay, so node at the closed end and antinode at the open end. You can write this down, or you could just draw the picture. This is when you have a sound wave in a pipe. got that? Okay, come, I can continue. Now, yeah. Close and open. Let's have a look. So, this is for when it's closed. When it's closed and open, the biggest wave you can fit is 1/4 of a wave. So, for example, if this is 1 meter, then the wavelength will be 4 meters. Okay. The next biggest one is 3/4, and then 5/4, 7/4, 9/4. Now, I want you to notice the names here. This one does not go 1, 2, 3. We call this the first, the third, the fifth, and the seventh. Okay. In this one here, when it's open and open, the biggest wave you can get is half. Then the next one is 1 wave. Then the next one is 3/2, and then 2, and then 5/2. Don't worry about this word here, overtone. We don't use that. We just look at harmonics. Now, how can you help remember this? Because here it goes 1, 3, 5, 7, and here it goes 1, 2, 3, 4, 5. I think I'll give you a minute. See if you can figure out a way to remember that this is 1, 3, 5, 7, and this is 1, 2, 3, 4, 5. How could we figure out the number here? So do you see any relationship between what's happening? Any ideas? Yeah.
The left is over 4 and the right is over 2.
Good. So for these ones are over 4 and these ones are over 2. And do you notice how for the third harmonic you have you have 3/4, and for the fifth harmonic you have 5/4. And in this picture here, the second harmonic you have 1 wave, which is like 2/2. And this one here is 3/2, and this one here is 4/2. Yeah?
How can we know which one, if, like the question said, fifth harmonic, would they say close or open?
Oh, they have to, yeah. So the question might say closed and open. Draw the fifth harmonic. So the fifth.
Draw.
Yeah, the fifth. Draw this. So the fifth harmonic is 5/4. Okay.
We can remember the number, but we can't remember the shape. How can
I'll help you. Okay. So look, before I continue, I just want to point out this is called the third harmonic because you can have 3 of the first one. See, the first one's a 1/4 wave. So we call this third because you can have 3 of the first one. And for example, this one is called the third harmonic because you can have 3 of the first one. The first one is a half. Sure.
Can we just see together?
What do you mean?
1/4 and add 1/4, add 1/4, add 1/4.
Oh, for this?
Left, right.
Oh, like that?
Yeah.
Oh, I don't like that. But if that helps you remember, that's okay. Look. Let's take an example. So let's say I ask you to draw the fourth harmonic in this closed and open here. Okay, so step 1.
Do we have this? It's 1, 3.
Oh, sorry. That is true, we don't have this. This one here. Okay, step 1. What is the biggest wave you can fit in here? So you must have anti and you must have anti-nodes. Okay, so that means you must have this and you must have this. So I think the biggest wave I can fit is this guy. Right? This one obviously no good. It's too small. I think the biggest one I can make is that. How much of the wave is it? That is 1/4 of the wave, isn't it? Peak to, crest to trough. There's only 1/2. 1/2 from crest to trough, because it needs to go back up the crest again. So the fourth harmonic should be 4 of those. So that would be 2 wavelengths. So let's try and draw it now. So I need to make 2 waves, but I must start with an anti, and I must finish with an anti. Okay, so start with an anti, and I need 2 waves. So let me just help myself here. Okay, I need to go from crest, trough, crest, good, okay, crest, trough, crest, and then it's vibrating up and down, so then you have the other direction here. So this is the fourth harmonic in a double open pipe. Now let me check my picture. Yeah. 1, 2, 3, 4, 5 antinodes. 1, 2, 3, 4, 5 antinodes. Yeah. It's not too difficult, I hope. Is it?
So could you give another example for the close and open?
Yeah. Let's go to the 5th harmonic, and in the open close. Yeah? Right, so firstly, what is the biggest wave? Well, this one must be a node, and this one here must be an antinode. So I think the biggest one I can put in is this guy, 1/4. That's the biggest one. So the 5th harmonic should fit 5/4 the wave. So that's 5/4 the wavelength. Okay, let's try and draw that. So I'll help 1/4, 2/4, 3/4, 4/4, 5/4. Node, antinode, but it must finish here. That's one wave. That's the middle. Okay, so up, down, up. There we go. And we get that picture there. 1, 2, 3 and a bit. What? Oh, sorry. 1, 2 and a bit. 1, 2 and a bit. Okay. But before we continue, imagine that you put some sand, sand, like the dirt you put at the bottom. What will happen is the sound will hit the sand here and push it away. But because this is a node, then the sand doesn't move here. So if you put some sand in the pipe, what will happen is you'll get a little pile here, and a little pile here, and a little pile here. Because what will happen is the sound will push the sand out. And this way you can see the nodes, because that's where the sand will collect. Yeah. Okay, now look. The only thing you don't need is this word overtone. It's a word from music. It's not important for physics, okay? We need harmonics, fundamental, and we need the pictures. Yeah, okay. You should draw at least 3 of them.
Each of them?
Each of them. It's good. It's practice. Help you remember. Try your best, Ben. Got it?
Disgusting.
It's not so bad. Continue? Okay. Now, there is a problem though. We have this thing called end correction. It's a short distance added to the actual length of the pipe. In pipes, the antinode is not formed exactly at the open end. Rather, antinode is formed a little distance away from the open end outside it. There's no reason, there's no formula for correcting it. So I'll explain what this is. The problem is this. I know in the picture it looks like the antinode is here, but really it's actually, let's try that again. Oh goodness. It's actually, it can be a little bit outside. So for example, let's draw another picture here. Let's draw this one. Let's just say this is 1 meter. Okay. So we think it's here, but really what happens is it can sometimes be a little bit outside. So the wavelength, lambda, is not equal to 4 meters. It's actually going to be a little bit more than 4 meters. Yeah? And the reason for that is because the L is not 1 meter, but instead it's really 1 meter plus a little bit. Delta L. So this guy here, we call this the end correction. Now the reason for this is not clear. So there's no formula for this. There's no formula to calculate what this is. But it's usually quite small. Like I think, for example, it's usually about, what is it? I can't remember, but it's usually equal to the diameter over 3, where this is the diameter. Roughly, okay? So, if you want to make this small, then your pipe needs to be a very narrow pipe, okay? If you have something like this, then this would be a big error, okay? So I think what you could do is just, you could just draw this picture. That's enough. Oh, yeah, okay, we'll have to continue this lesson next time. How much? We only have 1 hour now.
ICT.
You have ICT next?
What is
Computer class.
But what should I do? Like maybe
Who's your
someone-
teacher?
No.
I think it's presentation.
But we already done it.
Yeah.
Finished?
Yeah, engineering is done. Maybe he got another chance.
Yeah, my presentation time is in this afternoon.
Oh, this afternoon.
Yeah.
Can I close this, Gal? Okay, we'll continue it next time with some examples.